Hi, and welcome to this video on the topic of background radiation. When we talk of nuclear radiation, we tend to think of atomic weapons and power stations, and perhaps those little radioactive sources which your teacher may have used in school, but we're actually exposed to radiation from lots of other sources too. This so-called background radiation is always present around us, and before you get too excited, don't worry. The chances of it having any effect whatsoever on your health are even lower than your chances of failing your physics papers after subscribing to my GCSE Science. Over the next few minutes, we'll talk about each of the main sources of background radiation which contribute to the radiation dose received by the average person in the UK. Amazingly, about half of the background dose we receive comes from one source alone, radon gas. Radon is a naturally occurring alpha emitter which is released by certain types of rock. When this gas builds up inside buildings, it can cause a serious health risk. Being a gas, radon can be breathed in. Although alpha particles have a low penetrating power, remember that it takes just a piece of paper to stop one. They're very strongly ionizing and have a short range, which means that they deposit all of their energy within the body. This energy can cause cells within the body to stop working correctly, die, or mutate. Luckily though, radon gas levels only become dangerous in buildings in specific areas which are poorly ventilated. Moving on, we get around a seventh of our background dose from the radiation which is emitted by other radioactive substances which are found naturally in the ground and in building materials. Roughly the same background dose comes from medical procedures such as X-rays and a range of other diagnostic tools and treatments. The food and drink we consume also contains very small amounts of naturally occurring radioactive substances, mainly in the form of potassium-40, with Brazil nuts and bananas being some of the worst offenders, but the amounts involved are so small that this is probably a pretty poor excuse for wanting to go on a diet. About 10% of the background dose we receive is due to cosmic rays from space, which come mainly in the form of protons, other charged particles, and gamma rays. We're largely protected from this radiation by the Earth's atmosphere and magnetic field, but it can pose a significant health risk to astronauts. Finally, perhaps surprisingly, all other sources combined, including the fallout from past usage of nuclear weapons, nuclear accidents, and the ongoing generation of electricity in nuclear power stations, are responsible for less than 1% of the background radiation dose which the average person in the UK receives. To put these figures into perspective, radon gas is about 100 times more harmful to you than the nuclear boogeyman is. Let's finish off now with a quick example. We can see here that the count rate due to background radiation is 3 per second, but when the physicist places a radioactive source in front of the GM tube, this increases to 83 per second. That means that the number of counts per second due to the source alone must be 83 minus 3, which gives 80. For part B, we know that the reading due to the source alone was 80 per second at the start. After one half-life, this will have fallen to 40 per second, and after a second half-life, it'll have fallen again to 20 per second. At this time, the reading on the rate meter due to the source and background radiation will be equal to 23 per second. So we can see that two half-lives take half an hour or 30 minutes, which tells us that the half-life of the source is 15 minutes. That brings us to the end of this video on background radiation. Thanks for watching, try the exam style questions, and good luck.